This is the Texas A&M Senior Design Project for the Powertrain Selection Algorithm for Siemens Oil and Gas mobile app.
Hello? Yeah, Siemens. I need to get this gas moving. You guys got a gas driver for me? Yeah? You need what? Yeah, okay, hang on 1 second.
Have you ever been in this situation where you need a quick powertrain solution estimate, but the in-house tools just aren't fast enough? Our team has developed an algorithm to quickly estimate a driver selection. The design opportunity presented is that Siemens needed the ability to reach new customers using a powertrain sizing mobile app. This is a joint project consisting of one mechanical engineering team and one electrical engineering team. The mechanical engineering team's project task was to develop an algorithm to support a faster and simpler product selection tool, which is intended to improve customer engagement and enhance product positioning. The first step of this project was to develop the requirements needed for the app, with the most important one being that there would be a limited 7 inputs compared to the original 30 inputs that is used currently. From there, a functional model was formed as the basis for the algorithm. The desired outputs of the algorithm are the temperature out, polytropic head, and the power output of the compressor. In order to obtain these results with the limited inputs available, estimations had to be made for the polytropic coefficient as well as the gas compressibility factor. After obtaining the polytropic head and power outputs, the final outputs can be obtained, that being the compressor map, the gas turbine selection, and the power graph. All of the outputs to the algorithm and the different graphs produced were then combined into one Excel tool, colloquially known as the GF tool. With 160 different test cases available to test the accuracy of the developed algorithms, a comparison tool was also developed in order to more quickly get results and perform an error analysis for each case. With the comparison tool, it was much easier to employ an agile development strategy in order to hone in on what was causing errors and testing possible solutions. In general, the algorithms performed well when comparing the temperature out, with the high errors being caused by gases which are not commonly found in the midstream market. The same thing can be said for polytropic head error. However, the average error across all the cases are much lower, with 3% being the average. Continuing with the trend, the power output also shows that non-midstream gases average a higher error than common midstream gases. If we focus only on the midstream cases, the error drops to under 2% on average, which is excellent as this is a mainly midstream focused app. With a 95% confidence interval, the algorithm will average a 9.3% temperature out error, 3.9% polytropic head error, 13.1% power output error, and most importantly selects the correct driver 92.5% of the time across 160 unique test cases. And now, for a demo of the final product. The algorithm features a simplified 7 inputs that works with both metric and customary units. The power graph and compressor map show estimated operating parameters of the chosen solution. After a correct selection, the app prompts the user to save it and contact Siemens for additional information.
Hello, yeah, Siemens? Yeah, I need a gas driver that I just found on your app, the SGT400. Yeah, that's great, man. Can you guys ship that as soon as possible? Thank you.